So let's examine the actual experimental spectrum. Let's examine it more closely. There's a nice simulation at phet.colorado.edu. So let's take a look at that. Let's see, chemistry, blackbody radiation, blackbody spectrum. So here's the blackbody spectrum. Okay. So here's what the experimental spectrum looks like as a function of temperature. Okay. Right here. And so this is for 4800 Kelvin. You'll notice that the strongest light that is being produced by your blackbody is in the visible region. So you can see this object. It's going to be glowing because your eyes can detect the visible radiation. What happens if you go down to lower temperature? What happens to the intensity? It's less intense. Okay? And what happens to the peak wavelength, where the maximum wavelength that is producing? It shifts towards the longer wavelength. Okay, so it becomes invisible, right? It goes beyond the visible. Eventually, what happens? Let's go to about room temperature. What's room temperature? 300 Kelvin, right? So let's go down, down, down. Let's zoom in. Let's zoom in our scale here. So this is really gone down now. Okay. Let's do 300 Kelvin. Okay. See, the peak is already occurring way past 3 micrometers. Okay, so let me raise that up. Oops. See. So right here, so that's at 2000 Kelvin. So you can see it shifts to the right. Not only does it get weaker, less intense, but the peak wavelength, the wavelength where you have the peak in your emission, shifts to longer wavelength. Okay? Now, the spectrum that comes out from the sun and from a light bulb resembles that of a black body. So you can actually use the spectrum that you would record from things like the sun or a light bulb as a way to estimate the temperature. So what would be the estimated temperature of the sun then? About 5,700. What's the color that you see from the sun? It's around yellow, right? Yeah. Your eyes perceive yellow. It's really a mixture of all of these colors right here. Okay? And your light bulb? You still see some yellow from your light bulb. Okay? Not sure. That's what you perceive as the color. It's a mixture of all these wavelengths, and what your eyes will perceive would be that yellow color. All right. Now, what would be, if you were the only thing that's generating light? Okay, so you're in a completely dark room in a way. What would you be able to see yourself, or would somebody be able to see? No, because at 300 Kelvin, what's the peak intensity? You can see there's very little. You generate very little visible radiation. What you generate is actually in the infrared range. Okay, and that's why if you want night vision goggles, okay, you want to see in the dark, you need an infrared detector. All right. Okay, so let's see. What happens to the overall intensity as the temperature increases? What's the answer to this question? As you heat up an object, what happens to the overall intensity? It increases. In fact, it goes up to the 4th power. Okay, so power per unit area, that's intensity, right? That's joules. Power is joules per second. per unit area, so that's joules per second per square meter, or that's a watt per square meter, right? So that's directly proportional to the fourth power of the Kelvin temperature, and the proportionality constant sigma right here is 5.67 times 10 to the negative 8 watt per square meter per Kelvin to the fourth. This is known as the Stefan Boltzmann's law. Basically what it's saying is the hotter the object, the more intense the radiation. And what happens to the peak intensity? Does it shift to longer or shorter wavelength as temperature increases? It shifts to, let's see, let's go back. As the temperature increases, it shifts to, the peak intensity shifts to the left, right? Shorter wavelength or higher frequency. So peak intensity shifts to shorter wavelength. Okay? This relationship, the lambda max, where that peak intensity occurs, okay? Where that peak intensity occurs, like at this particular temperature, lambda max would be right around here. So this wavelength right here would be your lambda max corresponding to this temperature right here. So lambda max and temperature, we say, are inversely proportional. The higher the temperature, what happens when you raise the temperature? The lower the lambda max. So just like your Boyle's law, higher pressure, lower volume, whenever the two things are inversely proportional, the product is a constant. Okay, so that relationship can be summarized by this equation right here. This is known as Wien's law. Lambda max, that's the wavelength where the maximum occurs, times the temperature is a constant, and that constant B is this value right here, 0.002898 meters Kelvin. Okay?